video as many as time you can until you understand the concept. Okay, so for your idea, I'll be giving this recorded video in the Google Classroom, and as usual we used to do in the last semester also. Please go through it, okay, and try to make the best possible use of it. Okay, so now let us begin with this Laplace transform. So before I begin with the Laplace transform, now it's my very important task that I should make it understand why we are studying this Laplace transform. Because without knowing why we are studying, so if we just go ahead with the study, I think which is of no use. So why we are studying the Laplace transform, and what was the requirement, and what is the importance in fact of the Laplace transform uh, in any of the field, so that we have to make a note of. Okay, so first and foremost, this Laplace transform, it is nothing but what, it is the operation, or you can say it is working as the operator which will be converting a function, any function, you can say a function into a simpler one, a function into a simpler one. So what is this? It is a tool, or it is a mathematical operation which converts one function into the another simpler function. It may be any function. For example, if you have the transformation of logarithmic functions, say for example logarithm of ab, I have one function, I convert this into further simpler, that is log of a plus log of b. Or if you're having log of say a by b, sorry a, yeah, a by b, then it is log of a minus log b. So like that, what I'm trying to do is I'm converting the logarithmic functions into multiplication functions or division functions, okay, or simple form of addition functions and subtraction function. For example, the logarithmic function of a multiplication can be converted into logarithmic function of the addition, and logarithmic function of a division function can be converted into logarithmic function of a subtraction. So one of the way, I'm just giving a hint. Okay, so this is how, this is a mathematical operation which is converting a function to the simpler form. Then how exactly this function will looks like? So this function will convert, say for example before it was f of t, then this will function, this function after doing this transformation, it will convert in the form of f of s. What is this f of t, f of s? I will teach you once I'll start with the definition. Okay, and here there was a French mathematician, and he was an astronomer also. I'm just giving, this is all for motivating you all for the chapter. Okay, so this is, he is the pure Simon Laplace, pure Simon Laplace. He is the basically a mathematician, as well as he was an astronomer who used this Laplace transforms for the first time in 1799. Thus, actually, this transforms are named after his name. That is Laplace transforms. Okay, so please remember. And actually, this particular concept is widely used by the scientists and engineers, and it is also, this particular concept is used in solving the linear differential equations with the initial conditions. Okay, and what is this initial conditions, what is this linear differential equation, all this I'll be teaching you once we start with this chapter. Okay, and then definitely this Laplace transform also will be used in to reduce the differential equation and in algebraic problems, and it's really very important tool, I can say, in solving the electrical circuit in AC. AC means in electronics and communication department. The in order to solve the electrical circuit and system problems, they are widely using this Laplace transforms. Okay, and now in data science, because artificial intelligence and machine learning is like coming like a hub. So in the machine learning, again, in order to make the complicated functions to the simpler functions, to make it into the simpler functions, we are going to use this Laplace transforms. You name any fundamental area, so there we are using this Laplace transform. Okay, so this is just a background I wanted to give why you are studying this Laplace transform. Okay, so guys, being an engineer, now already you are an engineer. I don't say that now once you have passed out only you'll become engineer. Already when you're in a field, you have to feel that yourself as an engineer. So as an engineer, guys, it is very important fundamental thing that you should know Laplace transforms. Okay, applying stuff you will get to know once you will become used to that field. Okay, so but you have to have this as a tools. Now you're all setting the tools, you're developing your skills. So this is an additional skill. Last time you developed your linear algebra skill, and now you're developing your Laplace transform skill. So like that, you have to add your profile, you have to make your profile rich by making the additional skills. Don't forget the linear algebra which you have studied, because that all the concepts which you're going to utilize now also. Okay, so now let me come back to the definition. So here guys, we have many integral transforms. There are many integral transforms. So for example, if I have say f of s is equal to a to b kt into f of t dt. Okay, so this is one of the integral transform where this k of st, it is a given function with the parameter s and t, with the parameter s and t. This is also called as kernel of the transformation. This is also called as the kernel of the transformation. And here you can see this limits a and b, they may be finite value or they may take the infinite value. They may take the finite value or they may take the infinite value. Okay, so this is in general integral transform. The integral transform, it is a relation, it is a relation of the form k of st into f of t dt, where this k of st is called as kernel of transformation. If I'm not wrong, you have studied this transformation in the linear algebra also. So in the linear algebra, which kind of transformation do you have studied in the last classes? In the third module, in the beginning, what you have studied, guys? Is it not the linear transformation?
Yes, ma'am.
Yeah, so the same linear transformation we are going to apply here as well, but we are applying it for the functions here, particular functions. See, kernel, this also we have studied in the last class, I mean in the linear algebra. Here also we are studying. So what I'm trying to say is there is a connection wherever you go. I did not. I have already started recording beta. Don't worry. So wherever we go, so this particular linear algebra will follow us. That's what I want to say. Okay. So please remember, it's not about that. It is not about the null space here. It is a function here. This is called as kernel of a transformation, and where s and t, this s and t are the variables. Okay, and this is the kernel of the transformation. So whatever you're talking about the null space is not the kernel. Okay, don't misunderstand the concepts. Now the relation transforms the function f of t into another function f of s. This is called as the transform of s. Transform means what? Transformation. So this f of t is transformed to the function f of s. That's why it is called as transform by means of what? Integration. Therefore, it is called as integral transform. In particularly, when you come to the Laplace transform, how actually we will define it? Let us see. So here, let a real valued function I consider as f of t. Okay, so for given that t is greater than 0, now the Laplace transform of this function, it is denoted by, you please remember, it is denoted by, you can write the flower bracket, L of f of t is equal to, or it is also written as f of s, no problem. It is defined as integration 0 to infinity. Now see, a to b is converted with what? Here a is 0 and b is infinity. So it is 0 to infinity e to the power minus st into f of t dt. So in place of k of st, what I am having? In place of k of st, I am having e to the power minus st. So please remember, in the Laplace transform, the kernel of the Laplace transform is e to the power minus st. E to the power minus st will be the kernel of the Laplace transform. Okay. So and in the example or in the examination for 1 marks, if they ask following is the kernel of the Laplace transform, they may give you e to the power minus st, they may give you e to the power st, or they may give you k of st itself, or they may give you none. The answer is e to the power minus st. So please remember, and wherever you, if you remember this formula, I mean this is f of s is equal to, in general, for the integral transform. In that, if you are giving specific value to a and b, and your k of st, if it is replaced by e to the power minus st, then it is as good as, yes, it's a integration, it's an integral function. Laplace transform is also integral transform. In that, k of st is replaced by e to the power minus st. Okay, so this definition you have to remember. So this is the definition which is very very important as a Laplace transform. Whenever this improper integral, the 0 to infinity is an improper integral, it converges, we call this as the Laplace transform. And remark I have given, the kernel of the Laplace transform is k of st, which is equal to e to the power minus st. So here what is important is to remember the definition. Okay, now let me solve one simple example where how we find out the Laplace transform of the functions. So clearly you can see guys, f of t is equal to, they have given as 1. They ask us to find out the Laplace transform of this function, and they have given t is greater than or equal to 0. Now Laplace transform of what I want 1, where f of t is 1. So this is nothing but what? F of s. F of s, this is equal to 0 to infinity e to the power minus st into, this is our definition, right? F of t into dt. So this is the definition of a Laplace transform. Now what is my f of t? It is equal to 1. So wherever f of t is there, substitute that. And moreover, I'll just tell you, whenever you have the improper integral, for example you have an improper integral 0 to infinity, say f of x into dx, this can be converted into the proper integral by using the limit theorem. Say limit as a tends to infinity 0 to a f of x dx. Now what I am trying to do, this infinite limit I am converting into the finite one by taking that limit a is tending to infinity. This is very very important formula which I am going to utilize when I am solving the problems. Okay, so remember, if you are having a function of this form, now you can see here 0 to infinity is there, e to the power minus st into f of t dt is there. So this I am converting into now limit as a tends to infinity 0 to a e to the power minus st into f of t dt, into f of t dt. Okay, so this is how we are converting the given problem. Okay, so this is what, this was the improper one, I am converting that into the proper one. Okay, so now what I do, I consider this. Now it's a now see what is my f of t, it is equal to 1. Now apply the limits is 0 to a, this is limit as a tends to infinity, this is my e to the power minus st as it is into 1 dt. Why this 1? Because f of t is what? F of t is 1. Now it is a simple integration. So it is just integration e to the power minus st. Now it is nothing but e to the power minus st upon minus s. This is the integration of e to the power minus st. Now apply the limit from 0 to a here and limit as a tends to infinity. Okay, so if I apply the limits, you can see guys, here wherever this wherever t is there, I'm applying a. It is minus, already I have this minus sign. It is e to the power minus s into a upon s, and already one minus sign is there. Lower integral, when you are substituting, it is minus of minus, it becomes plus here, e to the power 0. S into 0 is 0 divided by s. Limit as a tends to infinity. So here guys, if you see, it is e to the power minus e to the power minus sa divided by s is there. If I apply the limit a tends to infinity here, this is e to the power minus infinity. E to the power minus infinity is nothing but what? 1 upon infinity. 1 upon infinity is what? It is 0. That implies this complete term will become 0. This complete term after applying a to infinity, this will become 0. Here you can see. Okay, and similarly what is remaining here, it is 1 upon s. So limit as a tends to infinity, this is 1 by s, because plus it is 1 by s, and here it is minus e to the power minus s upon s. As a is tending to infinity, this value will be, okay, 1 minute, 1 minute guys, somebody I think has come, right? There is no one with that USN number. Okay, fine. This also you take care, guys, from tomorrow. I mean, in the next class onwards, if anybody is joining, let me know quickly so that because they have no other work to do with what to do with them. Now see, he has just left the meeting. Okay, fine. Okay, now what I was trying to say here, this particular value, you please remember whenever you get the values like e to the power minus infinity, so this value will be tending to 0. So here this value will be tending to 0. So you have left with 1 upon s. The answer is 1 upon s. This is true for all s greater than 0. So therefore, the Laplace transform of this one is 1 upon s. These are all simple examples, guys. I think this example is clear. Let me know.
Ma'am, can you explain from the limit step again, ma'am?
This here from here you want or from here what?
No, ma'am, no, ma'am. In the example for
Okay, so see,
yes,
when
minus f, ma'am.
see whenever you're applying the limits here, this is nothing but wherever a is there, you have to apply the limit. Now see, e to the power minus s infinity, because a wherever a is there, you have to apply it. So it is s plus this is what only one term is there, right? Then next is 0, already one minus sign is there, minus of minus it will become plus, therefore it is e to the power 0 upon s. So it is e to the power minus s infinity. E to the power minus infinity is nothing but 1 upon infinity. It is 1 upon infinity, which is equal to 0. Okay, therefore this particular value, as a is tending to infinity, this value will be vanishing. This is 0. So what you are left is e to the power 0 is 1 by s. Here I am writing. So limit as 1 a tends to infinity, this value is vanishing. You are left with only 1 upon s. Thus, it is Laplace transform of 1 is equal to 1 upon s. So you will get it, guys, when you solve step by step. Okay, so try to solve each step. I think it will be more clear. So I've not skipped any step. So I've just tried to give maximum steps as much as possible. Okay, though it is silly or whatever it is, I'll consider each step so that you should understand it better. Okay, so hope that
Excuse me,
what,
ma'am.
yeah.
Ma'am, there e to the power minus a s, no, ma'am. So a is like infinity, ma'am.
Yes, A is not like infinity. Before I told you, right? This is what I did. Integration from 0 to infinity e to the power minus st f of t dt was there. This is given thing. I tried to convert the improper integral into proper by taking 0 to a limit as a tends to infinity e to the power minus st f of t into dt. Now, wherever a is there, that implies it is tending to infinity. So, when you are applying the limits, you have to apply wherever a is there, that has to be infinity. Got the point,
Okay, ma'am.
Arham?
Yes, ma'am. Got it, ma'am.
Yeah. So
Ma'am,
hope,
and s is a constant, no, ma'am.
yes, yeah, yes is a constant, beta. Yes is a constant.
Okay, ma'am.
Okay. So this is one simple example I think I am able to solve today. Just I'll give a hint for the second example so that you can just be busy with solving this one example. Now here in place of f of t, I'm giving it as t. I'm in place of f of t, I'm giving it as t. So same procedure, L of t will become f of s, that is 0 to infinity, e to the power minus st. In place of f of t, I'm taking it as t into dt, which is equal to, again, by using the proper integral from formula, limit a tends to infinity 0 to a e to the power minus st into t dt. Now here a small trick, guys. So this trick you have to use whenever you will be having your differentiation is tending to 0. Say for example, if I take t as a function, if I take the multiple differentiation, I'll tend it to 0. And this is for integration I'm considering, and cross multiplying with positive and negative sign. Okay, so that is t into this minus t into this, sorry, minus 1 into this. I'm doing and I'm applying the limit 0 to a, and then I'm taking the limit as it is to infinity, and I'm getting the answer. This just you check how I did it. Okay, because I'm going to explain this example again in the next class, but till today you have to see this, you have to go through this each and every step what I have solved, and you have to try yourself, you have to give a try. And moreover, I'll be taking your attendance screenshot in each of everybody every class once I complete the class. Okay, so you should not leave the class. You should not leave the class until I consider this attendance screenshot. Okay, and moreover, guys, 1 minute. I'll I'll just take a screenshot quickly. Moreover, till tomorrow's class, you have to, whatever I've covered today, you have to go through it and try to maintain your separate notes. Don't just take a xerox of my own notes. Okay, you have to practice it. Make a practice problem book separate, make a notes book separate, and try to do it today itself. Don't go for the next notes now only. Just to see the problems, one or two problems, you try to solve it. Each step I've given, try to solve it, guys. And I will solve the next part in the next class. And don't